In this video, I would like to give you a very brief introduction to thin layer chromatography. We abbreviate this TLC, okay? So a thin layer chromatography. It's a separation technique that is used to separate compounds on large gram scale or milligram scale if you're doing prep TLC. Also, it's an analytical technique. And this video here is going to complement any kind of TLC introduction you can find in a laboratory textbook, okay? Chromo or color is where this first came from, the separation of colored compounds. The typical thing you might do is take some leaves in the fall that are nice orange or red, grind them up with some acetone, spot them on a TLC plate, develop it, and you'll get these orange spots that are due to beta carotene, which of course is the result of these pigments in leaves. Carrots we're familiar with, and other vegetables and fruits. And also you see the chlorophyll, the green spot. It's kind of surprising. Oh, I didn't know that the fall leaves still had chlorophyll in them. Yes, after you do thin layer chromatography, it separates the yellow dyes from the green dyes, you know, the colored components, and you can actually see the chlorophyll in there as well as a bunch of other stuff. So let me tell you what this is about. Normally we use, so there's two things. The mobile phase is the solvent that we use. And this pushes the compounds, or it elutes the compounds, okay? The stationary phase in today's experiment is going to be on the thin layer chromatography plate, and that's going to be silica gel or silica. This pen seems to be losing its power. Let me see if I can find one. So if you look at these thin layer chromatography plates, they're roughly rectangular, okay? And they look white, all right? If you shine UV light on them, they contain a dye, fluorosil I think is the name, that fluoresces green, okay? So if you look at it sideways, this is a blow up. This right here is glass, ordinary window glass that's non-porous, and that's the support for this thin layer. So that's where we get the term thin layer, and it's about 250 micrometers, which is 1/4 of a millimeter, okay? So very thin, and that's the silica gel. It's porous, it's polar, and it does not move. It's stationary, so we call that the stationary phase, okay? Interestingly enough, silica has the formula SiO2, and that's approximately the same formula of glass if you don't add all the additives. Here just represents a bit of the formula of silica gel or silica. It contains siloxanes, it contains silanols, there's lots of oxygen atoms, and there's OH groups. These can perform hydrogen bond donating and hydrogen bond accepting with other molecules that might have oxygen or nitrogen in them. For example, ketones, alcohols, amines, amides, things like that, okay? So this is part of the stationary phase. I'm just drawing a bit of the molecule, all right? So it's an extremely zoom in. Now let's just draw a ketone here. A ketone is polar, and so it also can hydrogen bond because there's a lone pair on that oxygen atom. So it's going to adhere or stick or have an affinity for the stationary phase. Now, if you add a mobile phase to this, like acetone or something like that, or ethanol or some other solvent that'll move that along, it'll push, okay? So let me show you first what the setup looks like. In a beaker, what we normally do is prepare the mobile phase. This is the solvent we use for that, okay? It might be an 80%, 20% mixture of ethyl acetate and hexane. Ethyl acetate has this formula. It's an ester, it's a polar solvent. Hexane has this formula. It's a nonpolar solvent. And we mix those in the ratio we, kind of, randomly determine in the lab to give us good results, okay? So that's just an 80-20 mixture, which I normally just start off with, usually. Okay, so you put a small amount of solvent in your TLC chamber, okay? So here's your mobile phase on the bottom of a beaker, okay? Ideally, it's nice and flat. And we want there to be vapors of that solvent in here as well. So we oftentimes cut a little filter paper and wrap it around the side of the beaker, okay? We cover this with a watch glass so that the solvent doesn't evaporate. Hexane is more volatile than ethyl acetate, so if these vapors evaporate, you're going to change the composition of the mobile phase in there and your results are going to be different, okay? So there's our watch glass, here's our beaker, a filter paper, and the mobile phase on the bottom. Now to prepare your TLC plate, and you'll see this when I do a demonstration, you always want to use pencil when you're labeling your TLC plate. The reason for that is because ink from an ink pen contains chemicals that are dyes that will show up on your chromatography plate, okay? So about 1 centimeter from the bottom of the TLC plate, you want to take a ruler and draw a line with a pencil, okay? Now, it should be a sharp pencil or a mechanical pencil, but you don't want to dig that in there and scratch the surface of the silica gel, which is quite loose and friable, okay? What you want to do is draw your line by holding it at an angle. Just slightly put pressure on there to drag your pencil across the surface, okay? If you try to write on it with a piece of paper, your pencil will dig in there and you'll just remove the silica gel. I like to use my pencil and make maybe 3 lanes, okay? Starting material, reaction, product, or maybe component A, component B, or component C, or maybe component A 3 times with different loading ratios, okay? Now what you want to do is make a capillary, okay? And over here on this table, I'm going to go ahead and make some capillaries, okay? So what I like to use is flint glass, but I don't have any today. I'm gonna use a borosilicate glass. So these are Pasteur pipettes. They have a pretty low melting point. So you wanna turn the gas on, all right? And the way to make capillaries, this is very relaxing and therapeutic, in fact. You want to point the flame right in the middle here, okay? Hold with your fingers, heat it up, pull it out of the flame, and then rapidly pull it apart, okay? When you put, I'm not sure if you can see this on the camera, but the inner cone of the flame is going to be right there. You don't want to put it too low or too high, okay? You want to put it like right around there, okay? So the inner triangle should be right underneath your glass. And you want to rotate it slightly, okay? And I'm twisting my fingers here to cause it to rotate. You'll see as the glass heats up, you'll see an orange flame, and that's due to the sodium ions emitting their characteristic color. You know, when the excited ions, the electron transfers to a lower energy state. They emit light in this color. So, you know, you can kind of feel the glassware bending there, getting loose. Flint glass is much better because the melting point is much lower. But here we're using borosilicate glass, so I have to do this for quite a while. Okay. When you feel the glass very soft here, I don't feel it really soft. We'll just try it anyway. Pull this out and then rapidly stretch it, okay? And so what we have here is a very thinly drawn tube, okay? So now what we can do is let this cool, of course, and then we could snap it into 4 or 5 or 6 pieces, okay? So I'm gonna make a couple of these now that I got this flame going, and we'll come back to the video and keep introducing this thin layer chromatography in a bit. All right, so the way to prepare the TLC plate, as I described before, is to draw a pencil line, draw 3 lines, and then what you want to do is take a test tube that contains just a small amount of your analyte, okay, the thing that you're analyzing. Dip the microcapillary into the solution, and by capillary action, it'll be drawn up into the tube. And then you want to hold this over the TLC plate and spot briefly once on the baseline, okay? On one of those marks. All right, and what happens is by capillary action, it draws into the porous silica gel. Now you don't want to hold it for 5 seconds and make the spot the size of a nickel. You want small spot sizes, so you just want to tap it right on that spot and make a small spot, about 1 millimeter or 2 millimeters in diameter maximum. You can withdraw your tube, gently blow on it with your breath to evaporate the solvent that analyte is dissolved in, and then reapply it again, blow, reapply it again. So what I like to do is 1 spot, 3 spot, 5 spot on those 3 different locations, okay? So I have the least amount of material, 3 times as much, and perhaps 5 times as much on that right-hand lane. Then what you do is you make sure all of the solvent has evaporated from the TLC plate that you use to spot your compounds onto, and the compounds are non-volatile, okay? Those could be Vinca Alkaloids, that could be cannabis oils, that could be chlorophyll we mentioned, or beta-carotene from flowers, something like that. So you're gonna use forceps, okay? Tweezers. You're gonna use forceps to hold your TLC plate. You always wanna hold the TLC plate on the edges because there's chemicals in your fingerprints and things like that, okay? So hold this with forceps, remove your watch glass, you're gonna put it in here and close it, okay? If your baseline is below the level of the solvent, it's not going to be able to push it up, okay? Now your mobile phase, because of capillary action and the porous nature of this silica gel, will gradually move up the TLC plate. And that's why we call this solvent the mobile phase, because it technically moves, okay? As it passes through your compounds, it's going to move them depending on the polarity and so on of your molecule, okay? So at the end, you're gonna get the mobile phase all the way up to the top, about 1 centimeter from the top or so. And what you wanna do is remove your watch glass, use forceps to grab just the dry portion here, pull that TLC plate out, and then promptly take a pencil and then mark a line right here before the solvent evaporates, because you won't see it anymore, okay? You want to let this air dry out on the countertop, or if you're in a rush, you can put it on a hot plate at a moderate setting, okay, for just a few seconds, and then pull it off, okay? So all the solvent will be removed, but again, those analytes that you're trying to visualize will not evaporate, okay? Now, if you do this with a colored pen or a felt tip marker or something like that, afterwards you should see some colors like red or green or dark blue or something like that, okay? In the case of colorless compounds like aspirin or something, something that's white crystalline is just going to be colorless. It's not going to be able to be visualized on this white silica gel background, okay? So there's different ways to visualize the TLC plate. But let me show you what's going on here with the mobile phase, okay? So if we have ethyl acetate, as the mobile phase, okay, this is going to pretend like this TLC plate is actually in the solvent this way, okay? So it's moving this way from left to right, okay? Now we mentioned that this ketone is hydrogen bonding to the silica gel surface, so it's tightly adhered. But when the mobile phase is going through the solvent, that molecule can hop off, interact with the mobile phase through dipole-dipole interactions, and move a little bit. Before then, it readheres or reabsorbs to the silica gel surface, okay? So there's an equilibrium. It's kind of like hopping, okay? It's desorbing and then reabsorbing and desorbing and absorbing and so on as the mobile phase is pushing it across the silica gel or up the silica gel, okay? Molecules that are strongly adhering to the silica gel are highly polar, they're hydrogen bonding, and they're going to show up with a lower position here on the TLC plate. Okay. So this is going to be something that's hydrogen bonding. It's going to be something that's polar. Okay. For example, reposition the camera here. For example, something like this, okay, which is a carboxylic acid, okay, maybe an alcohol, okay, maybe a ketone. I'll just put some random stuff on that molecule, okay? So these top two are polar and hydrogen bonding. This bottom one is polar, okay? So those are going to be down on the bottom. They're going to be more polar because they adhere to the polar stationary phase more strongly. At the very end of the spectrum, you're going to have non-polar molecules or less polar molecules. Everything's polar to some extent usually, but I'm just going to say non-polar to make it black and white, okay? Your non-polar analytes are going to be things like aromatics, hydrocarbons, stuff like that, okay? So an example of that would be maybe terbutylbenzene, okay? This guy right here has no oxygen or nitrogen for hydrogen bonding. It's not going to adhere to the silica gel very strongly. It's only going to do so by action of London dispersion forces. So very, very weak intermolecular forces are going to cause this to stick to the silica gel. When the mobile phase comes through, it's pretty much just going to wash it on through very quickly because it's going to hop up or desorb from the silica gel. The mobile phase is going to push it quite a ways before it decides to come back down and explore the silica gel again and then come back off. And the mobile phase is just going to push it through very, very quickly. Okay? So more polar things on the bottom, less polar things at the top. You should be connecting this with chapter 2 or 3 in your first semester organic chemistry class, which talks about intermolecular forces. There are 3. The strongest force is hydrogen bonding. The middle force is dipole-dipole forces if you have a polar molecule. And the third and final weakest force is London dispersion forces. Okay? So you should know about those, and you should know that the more intermolecular forces are going to make a molecule lower on the TLC plate, and less intermolecular forces is going to make a molecule show up higher on the TLC plate. Okay? Now, the position of your spot is going to depend a little bit on the mobile phase as well as the nature of your molecule. Okay? So the type of mobile phase does play a factor. So let me show you what that looks like. So here's the same compound. Let's just make something up. Let's just call this ethyl benzoate, okay? So here's the analyte. It's a material that's polar, it can be hydrogen bond accepting, but not hydrogen bond donating because it doesn't have a OH bond, okay? So it can be quite sticky to the silica gel surface. Over here on the left, we have ethyl acetate, which is the mobile phase, and that pushes the spot up quite well because it's very polar, okay? It competes with the silica gel, and this molecule might decide to dissolve or desorb or be dissolved into the ethyl acetate as it's moving through the TLC plate and pushes it across upwards quite fast, okay? Over here on the right, we have hexane. Hexane, as you know, is a non-polar solvent. It really does not look like an attractive place for this molecule to dissolve because like dissolves like. This is a very polar molecule. It's more likely to be just staying in the silica gel, which is very polar and compatible with the analyte. So hexane doesn't have as much eluting force to cause this molecule to travel or move up the TLC plate, okay? Now we have a way to quantify the position of these spots. We call this the retention factor. The retention factor is a simple formula. We normally have 2 decimal places here for the number, and it's going to be the distance the spot traveled divided by the distance the solvent front traveled. Okay, so if we take a look here, we'll just do some rough math with this ruler here in centimeters. On the TLC plate, I would measure it in millimeters. Okay, so here on the board, since it's so enlarged, I'll just do centimeters. So the solvent front is the distance between the baseline and the solvent front. So this is the total distance that the solvent moved, okay? So this is the distance the solvent front traveled, all right? And so we measure that distance, and here it's going to be, we're just gonna say 18, okay? 17.5 centimeters. And then what we do is we measure the distance the spot traveled. And that's this distance here from the baseline to the center of mass, okay? So you don't measure the bottom of the circle, you don't measure the top of the circle, you kind of guesstimate where the middle is, which is like right around there, okay? And so you take a ruler, metric ruler, plastic metric ruler, ideally one that's transparent that you can see through, and you position this here. I can't do it because the ceiling's in the way, but let me just do it upside down here. So that's 7.0 centimeters, okay? And then you calculate the ratio, so it's unitless, okay? The centimeters cancel, the millimeters cancel. So it's 7.0 divided by 17.5, and I normally report this to 2 sig figs. So the number is going to be between 0 if it doesn't move at all, and 1.00 if it moves all the way with the solvent front. So in this case, okay, I get 0.4 on my calculator. So I would just report it to 2 decimal places. That's what I like to do, okay? So that's the retention factor, okay? If you have a component like this example that we went over before with 3 different RFs, that's going to give you an idea of which compound might be more polar, okay? So I'm not going to measure this and compute the distances and all that, but I'm just going to throw out some numbers. So this has an RF of 0.92. It's higher, that means it's less polar, okay? Higher number, less polar. This is RF of 0.21. It's a lower RF, so we know immediately that it's more polar, okay? So if you go to literature and you look at a table of RF values and you have all these numbers, you know that the smaller RF generally means that it's eluted or moved less on the TLC plate, okay? I think I'll do a simple technique for you so you can see how this works, and then I'll show you the different methods by which we can visualize the spots, okay? we'll learn about how we can use UV light, we can use iodine, and we can use Hexane stain for that, okay? Or lots of different stains for that, but I'll just show you how that works later on. All right, so that's a very brief introduction. You might complement this or just skip this video completely and read the chapter on TLC. Thanks for watching, and we'll see how this works in the lab.